Welcome to the course Digital Transformation and Technological Innovation. So, today we are starting our fourth module, that is Tech Advancement and Internet Basics. So, let us start. Now, first question that we would be dealing with in this module, that is Tech Advancement and Internet Basics, is we will talk about how technology is advancing. So, in terms of processing capabilities and storage capabilities and networking capabilities, how the technology in advancement is happening, and we will look at some of these advancement rates and discuss many of the issues that have been there over a long period of time, right. So, we talk about the advancement rates of tech. So, advancement rates of tech, they are actually driven by the phenomenon of faster, cheaper computing with every successive generation of tech. So, every new generation, what we see a faster product, faster computing product and cheaper as well. So, faster, cheaper computing, right. So, this phenomena is very peculiar to computing industry, computing products, information products, and high tech products also to some extent, right. And this is very different from what we see in traditional products in a traditional economy space, right. So, we will try to understand some of these differences, the kind of phenomena that we see in case of computing product, information product, that is faster, cheaper computing with every successive generation, right. So, in traditional product, for new generation, the price might go up and the performance might also be, many people might feel the performance is also not equivalent to what was there in 2 years back or 3 years back or 4 years back. Performance in the sense quality, in case of traditional products, it would be more about quality of product or service. So, not only the traditional products, they become more expensive, their quality might also go down over the years. But in case of computing and information product, not only they become better in terms of performance or any other desirable attributes, but they will also become cheaper, right. So, this runs very different to traditional products, and that is why the economics and the whole tech business game is so much different from traditional businesses, right. So, driven by the phenomena of faster, cheaper computing with every successive generation of tech, and it is something that was observed by Gordon Moore, who was Intel co-founder. So, since then it has been referred as Moore's law. It is not more of a scientific reason to say that this is a law, it is more of a statistical observation that is there that actually captured this faster, cheaper computing thing that I just talked about, that computing products, information products, over the years they not only become cheaper, they also become faster, right. So, what this Moore's law is about, what does it say? So, it actually defines the chip advancement rates. This is Moore's law basically applies to chip manufacturing. So, it defines the chip advancement rate, and it defines the chip advancement rate based on the number of months taken to double chip performance per dollar, right. So, how many months it takes to double the chip performance per dollar. So, that kind of chip advancement rate, it is defined by the Moore's law. So, essentially the fast cheap computing that we just talked about. So, essentially this particular observation, a statistical observation by Moore, that captures what has happened in the industry and continues to happen. That means if you just observe the manufacturing of computing products, and you would see that in few months or 1 year or 2 year, you will see that the same product has improved, obviously with the change of hardware and the internal components. So, the same product has improved and has become cheaper. So, chip performance per dollar, right, that means chip performance per dollar, $1 that we spend, per unit dollar that we spend for chip performance, so the performance doubles. So, per dollar that we are spending today and the same dollar that we spend maybe a few months later or 1 or 2 years later, will get double the performance, right. So, this is what it defines. chip advancement rates based on the number of months taken to double chip performance per dollar, and this is what created the phenomena that we are referring as fast cheap computing, fast cheap computing in general. So essentially it also indicates exponential growth, because for a given number of months we are saying that the advancement will double or even more than that. So this actually indicates the exponential growth that can be observed there. So for example, in the 1970s, when this Moore's law was actually put down or written down or observed, 24 months, or now many sources refer to 18 months figure. So 18 months, approximately 18 months in the 1970s, that kind of number was observed in the 70s when this Moore's law was coined, right. That means in 18 months the performance per dollar that doubles, right. So if you can hold on to you can delay your purchase for, let's say, 18 months in 70s, then you will get a better computing product, right. So that means it has serious implication to CTOs and CEOs and CFOs and everybody, all the top management, that if they are planning to purchase a server today, and there is not much computing need that purchase server will immediately satisfy, then maybe they can delay the purchase, because few months down the line, or 1 or 2 years down the line, they might get a better server, better performing server with better performance attributes, maybe at the same price, maybe at even lower price, right. So that means the timing of investment and the kind of product that you are investing in terms of IT, information technology products or computing products, and also at the same time because of the lack of resources, lack of computing resources, you don't want to lose out on your market, right, the market that you are catering to. So that becomes a trade off as to whether to delay the purchase or whether to go for it, because you don't want to lose out on the market because of lack of resources and other things, right. Sometimes as a firm you might want to be the leader also, right. So for follower firms, it's quite easy decision that they can delay their computing purchase decision, but for the firms which want to lead in a particular industry sectors, which want to be the top firm in a particular industry sector, they might end up paying more, right. So whether that will benefit them in the long run, whether they will be able to hold on to the market share, or whether the follower will be able to quickly capture, and also because the follower was late in their investment decision, they got better computing support and at a lower cost. So there are such a complex there are so many complex implications of fast cheap computing that we are talking here. So advancement rates of tech, they have far reaching implications in the tech business, and even for the non-tech businesses, because now whether it's tech firm or non-tech firms, all kinds of firms, small to medium to large, everybody is using computing in one way or another. So therefore in a way it affects everyone, right. So exponential growth it is something that is observed in case of chip advancement rate. Now if we look at the historical growth, so we can look at the historical, whether what we just said, whether we can also observe the same thing looking at some data points that we have with us. So let's look at chip performance per dollar. We will focus on chip performance per dollar, and we will look at the historical growth. And what we have a table that that in a way illustrates this exponential growth by decade. So reference baseline for the microprocessor that we are taking is Intel 4004, that came in 1971. So taking Intel 4004 as a baseline, what I have done, I have used generative AI to actually retrieve some data, and that generative AI also used a combination of transistor density, clock speed, and architectural efficiency to actually estimate the cost of the hardware. So we got a nice table that we can use to compare and see for ourselves how this advancement rate has happened, whether the fast cheap computing is clearly visible to us just like it was to Moore. So let's look at these numbers. So retrieved using generative AI. So if we look at the 1970s, Intel 4004, that is our reference line, and that came in 1971. So we can see transistor per count to be 2300, much smaller in comparison to today's standards, as we will see as we go forward in the table. Then we look at the launch price, and this launch price is adjusted for inflation. So therefore this would be approximately 500 USD, and this is what we are considering as 1x, because this is our baseline in terms of approximate performance per dollar, right. So performance per dollar we have taken, and relative to 1970s, this is our reference model Intel 4041, and this was the launch price was 500 USD adjusted to inflation. And number of transistors, the number that we are looking at is 2300. Now if we look at from 70s to 80s, what happened, we got Intel 80386, that came in 1985, and it had how many transistor counts? So 2,75,000 transistors there, and the cost so you can see the jump that is there. So more than much more jump, if we just more than 100 times jump has happened. So you can see approximately 100x. So in 10 years or more than 10 years in a way, we will compare 71 and 85. So more than 100 times the performance improved, and if we look at the cost, then it was only 3 times. So cost was 3x, launch price 500 USD to 1500 USD, but performance jump was 100x, right. So from 3x you pay just 3 times more, maybe 15 years 14 years down the line, and you get 100 times better performance. So that is something that you won't see in traditional products. So that is the phenomenon of fast cheap computing. So it's not just cheaper, you get better. So you get better product, better performing product, you get at a much lower cost. We just look at the improvement there. So why that happened? Because manufacturing industry, computer manufacturing industry, they had some serious advancement in manufacturing technology, in production technology, and because of that they were able to pack more number of transistors in the same chip. So their ability to pack more number of transistors significantly improved, and because of that they could provide this kind of performance improvement. And this advancement in production technology, that means ability to pack more transistors in the same chip, that continued to improve, and we now compare 80s with the 90s, and from Intel 80386 to now we come to Pentium 3rd, that is 1999, and how many transistors here? 9.5 million transistors, that was the count in case of Pentium 3rd, right. And if you look at the price, you will be surprised, went down 1500 USD approximately to 1200 USD. That means from 2,75,000 transistors it went up to 9.5 million times, right. So from 100x to 10,000x, right, from 100x to 10,000x, and that is also if we take 80s, this particular number as a baseline. So this is also 100 times improvement, and the cost went down. So that means when you move from 85 to 99, the launch price is adjusted for inflation. So you pay less and you get 100 times better product. So there would be no other industry or traditional product which would be giving this kind of fast cheap computing impact, right, that we just talked about. So 100 times better and the cost goes down. So that was from 80s, 85, 80386 to 1999 Pentium 3rd, right. So obviously when this happens, so while the cost is going down and you are getting better products, so what will happen in the consumer segment, right? Obviously more and more people would be able to afford this, right, and there would be sudden demand for these products. So the demand for the products, because they are getting cheaper and also they are getting better. So two reasons, now they can afford, and they are getting a better product than maybe few years back. Others are still stuck with the same computers, but the new buyers, right. So new buyers benefit, right, because they, for some reason, their purchase decision was delayed and they benefit significantly, and the demand for every new latest product, there would be a hype all the time, right, because latest product is more likely to be better and cheaper. So therefore every latest product in computing industry that is coming from computing industry, there would be naturally be hype. And what is working behind that hype? The phenomena of fast cheap computing. That means you can clearly see 100 times better performance per dollar, and cost goes down, right. So this is a phenomena. This is something that happened 70s, 80s and 90s, and that is why if you correlate this with the internet penetration in the late 90s, why so many people, why so many internet users, why there was so much growth in number of internet users in the late 90s, because of this, because they could afford a computer which was doing quite well in terms of performance, and it was low cost, affordable. Moving on, now we come to 2000s. So 2006 model. Now here you see that we are the name is core 2 quad. So now here something else also happened, that now when you keep on packing more number of transistors from 2370s to 2,75,000 in 80s to 9.5 million in the 90s, when you keep on packing so many transistors on the same chip, then obviously in the pathways that are there, and we will talk about this in detail, it is the same space, same size, and you are packing more. So therefore there is more heat that is going to be generated. So therefore there was change in the design, chip design. We will talk about this later also in later slides also. There is a change in the chip design that happened, and it was core 2 quad and 582 million transistor count. So look at from 9.5 million to 582 million. So this design was obviously to deal with the heat that was getting generated because of packing 582 million transistor, which is many times more than what we earlier had, 9.5 million to 582 million, right. So that is about more than 50 times more number of transistors. So obviously heat would be an issue, and therefore the design change. Now we look at the launch price, which is already adjusted for inflation. Now it goes further down. See, it was 1200 USD earlier in the 90s for Pentium 3. Now this is much better, but the price goes further down, 1100 USD, and performance you see is way higher, 1 million x if we will take the reference line, right. So from here also it is 100 times better from the what they had in the 90s, and what we have mentioned for the 2000s, this 100 times better, and the cost goes further down, and number of transistors are much more, and there was a change in the design also. So you see the advancement in the production technology. They were able to pack more than 50 times transistors, number of transistors that they could do in the 90s. The cost also went down, performance improved 100 times better than in the 90s, right. So we are talking 2000s here, right. So from the 70s to 80s to 90s, and then to 2000s, you can clearly see that there is continuous improvement in the performance, and the cost is actually going down. Now we look at the 2000s, then there is another representative chip that these are representative chips. So obviously there could be comparable chips also during the same time. So you can see Xeon Ivy Bridge. So this came in 2014. Now we are into 2010s, and now 4.3 billion transistor count. So they could pack 4.3 billion transistors in this chip, and cost went up now, so to some extent 2000 USD. But if you look at the performance, this is 50 times 50 times more, 50 times more in terms of performance. So cost slight, we compare, but still if we look at the performance improvement, so it is still good, but if you see the rate of advancement, it's slightly slowing down in 2010s. So like 2000s, from 70s to 80s to 90s and 2000s, so the rate of advancement was much higher, and then there was a dip in the advancement rate. So advancement was still happening, 50 times better performance, and the price slightly up, which was earlier going down, right. But here all you can see that it is just 8 years that difference that we are talking. So that could be something to do with it, but still we can see, we can say that there is some sort of dip in the advancement rate, but still it is advancing, right. So fast cheap computing is still, that phenomena is working even in 2010s. Now if we talk about 2020s, then the representative chip is Ryzen Threadripper that came in 2020. Now see the jump in terms of number of transistors, 4.3 billion to 39.5 billions. So approximately 10 times jump, and price got doubled, more than doubled, from 2000 USD to 4500 USD. And if you look at in terms of the performance, then it is 10 times more, right. So there is performance improvement also, but now the dip is very clear. The dip in advancement is very clear here, right. So from 70s to 80s to 90s to 2000s, the advancement was very quick, and we saw huge amount of internet users during 2000s. Then the advancement slightly slowed down, but again one should note that we are talking from 2014 to 2020, that is 6 years. So earlier change that we were talking were like 14 years, and then here also 14 years, and then from 1999 to 2006, that was 7 years, and there was change in the chip design also. After that 8 years and 6 years. So but still we can say that there is slight dip that we can notice in terms of advancement rate, but still fast cheap computing is the main phenomena that has been pushing the computing industry, and therefore affecting all other industries, because all other industries, we talked about tech firms and non-tech firms in our earlier modules. So non-tech firms are consumers of the products from tech industry, right. So essentially this affects, influences everything else, right. So there would be more demand. So the point is that because of this phenomena that we can notice in this data set, there would be more demand at the consumer in the consumer segment, in the business segment, all segments, and why that is happening, that we understood, right. Moving forward, now the Moore's law that we talked about, so basically it applies to processing processing products that we talked about, mainly to chip, right. For storage and networking, the performance curves are also exponential, but obviously they are slightly different in terms of the advancement rate. So that will be taking later. Right now we talked about the Moore's law and the processing, and it mainly applies to chip. Now what are the products that are based on chip? So processors, microprocessors, and then the storage. There are chip based storage also. So when we talk about this observation that performance per dollar doubles 18 months, the original Moore's law, so obviously that 18 months the number changed from decade to decade, but right it also applies to chip based storage, not just microprocessors, anything that is chip based. So computing components that are made out of semiconductor materials, when we say chip based products, so essentially semiconductor material, silicon is being used in those products. So there this phenomena, this Moore's law applies to, and the performance per dollar doubles maybe in 18 months, 20 months or 24 months, those kind of numbers, right. Now moving forward, what are these chip based computing components? So one is random access memory, microprocessor was already there, we talked about. What are other components that are there? Random access memory is there, and then the flash memory, flash storage. Obviously there is some difference in terms of chip design for RAM and for flash, memory or flash storage, right. So, here we are talking two things, flash memory and flash storage, right, and the RAM. So, there is a slight difference that might be there in terms of chip performance for RAM and this higher quality chip for the RAM, right. So, now this flash memory and flash storage is something now connected back to that everything is price is going down, performance is improving. So, there would be more demand, and not just in the consumer segment, in the industry segments also. So, many industry segment they will start using the flash storage because that suddenly becomes affordable for their products. They will start using it in cameras, USB drives, so now we have flash USB drives, mobile phones and lightweight notebooks. So, all these computing products they were maybe earlier using different storage technology, and now they will go for the chip based storage, flash storage technology, and they will become faster in terms of performance, right, and in terms of life also. So, that also we little bit talked about in our earlier modules when we were talking storage, right. So, you can see that the impact how it travels to other industry segments, other products, right. The performance improves for chips, then that has an impact on RAM. People will have more RAM in their computers, or flash storage, people will be able to afford flash storage instead of hard drives, right. And in other computing products, cameras, USB drives, mobile phones, lightweight notebooks, they are also the use of flash storage, flash memory that will go up, right. So, therefore, the demand for that will go up, right. And so that this is the impact of the advancement rate and the fast cheap computing that we could observe with this. Now, how do we interpret this? So, again to rephrase something that I said in 18 months. So, we are again putting down some interpretations. So, in approximately 18 months, original Moore's law, next generation chips will be twice as fast, will cost the same as today's market, right. So, if you have certain budget and you do not have immediate needs or immediate impulse to buy a computing product, and you can wait, then you will get a twice faster product at the same price, right, in 18 months if you can wait. Now, in other words, if you are not looking for a faster product, but you are looking for the same product that is available in the market, but you do not have that much money to afford it, then again you can wait for maybe 1.5 years, and what you will see that chips matching the same speed as today's designs will be available for half the price. So, if you are looking to get the same product that you see today, but at a lower price, then you wait the same time period and 1.5 years in case of chip, and you will get it half the price. Or if you are looking for a product which is better than the today's design, then again you can wait and it will cost you the same and you will get a fast product. So, for different customers, different businesses, tech firms, non-tech firms, different kind of needs would be there. Accordingly, the interpretations they can apply, the managerial implications will be there, right. So, as we talked about, this makes tech products price elastic. So, the fast cheap computing phenomena makes tech products price elastic, and so what that happens, because the changes in prices will happen. So, there would be immediate impact in the demand, right. And while this price elasticity is very different from what may be observed in some traditional products, right, because the price also goes down, performance improves. So, that is also there. So, when we say price elasticity, essentially what we mean. So, now we are talking about what is the role of price elasticity in tech demand. So, price elasticity is what? The rate at which the demand for a product or service fluctuates with a price range, right. So, with a price change. So, if there is some price change, price goes down, so the demand will go up, right. But then in traditional products they are demand, supply demand constraint. So, while demand will go up because of the price change, then the supply constraint will kick in and then things will balance out, right. But in case of computing industry, that is not the case, because they will start producing more, and right. So, obviously the performance also improves, so the demand goes way higher, while obviously they will try to produce more to fulfill the demand, right. So, tech products are highly price elastic, and when I say they will produce more, because in traditional products there might be raw material constraint on raw materials which is coming from natural sources. So, there are constraint to what you can get from nature, or there is limit to something that you are sourcing from the nature. But in case of computing products, it is more of manufacturing production technology, and more mining, more processing can be done. And so, it has been observed that the demand and the consumption of computing products has been going up, and the industry has been able to fulfill much of that demand. So, tech products are highly price elastic. So, they are bought more as they become cheaper, right. And again, this might not be how many units of a traditional product you can buy. So, something that some product that you have been already consuming. So, there is much less hype or excitement about traditional products, even if there is some price elasticity that is being observed for a temporary period or something. In case of a tech products, there is much more excitement, because people want to try better performing computer, people want to try the best performing computer, and therefore, they would be willing to let go of their current computer, and they will be willing to buy a new one. And then there is a life for existing computer also. So, it might be wearing down, and performance might be going down, it might be becoming slowish. So, there is always there is always more than one reason to buy computing products. So, therefore, this demand and this price elasticity works very different in case of tech products, right. So, next generation tech gets cheaper, and the price elasticity that we talked about, that can kick in various ways. So, let us stop here, and we will continue our discussion in the next session. Thank you.